Hello, welcome. Today we're going to talk about conservation of momentum, or how does the momentum of an object change as that object undergoes a collision. All right, so what we're going to do is we're going to look at some of the data that we collected from the Interaction of Moving Objects lab, and we're going to use that to come up with this law of conservation of momentum. The key points or the key data that we want to look at on our lab is this ratio between the initial momentum and the final momentum. Okay, that is the key element that tells us how close, if any relationship, there is between final momentum and initial momentum. So if I look at this, if I take my final and I divide it by my initial, then the closer it is to 1, the closer there is to a relationship, or that there is this idea of conservation. Now, if the conservation is true, which it is, if I notice this one's 0.86, this one's 1.2, and this one's 1.1, if it's true, then these should be very close to 1. They should be almost exactly the same. Now, if you account for human error in our calculations, human error in our experiment, and mechanical error in our tools, then this is very close. And actually, this is true. There is a conservation principle to momentum. Okay, and so if we look at this, we can get the equation for conservation of momentum just like we got the equation for conservation of energy. So what this tells me is it tells me that my final or my initial momentum equals my final momentum. Okay, and that's total. My total initial equals my total final. Now I need to flesh this out and turn it into something that we can actually use to do predictions and use calculations or do calculations with. And so my initial momentum, my total initial momentum, this column right here, was obtained by taking my initial momentum from my first object and adding it to my initial momentum of my second object. So the initial momentum of object 1 plus the initial momentum of object 2. All right, and my final total momentum was this column was taken by adding up my final momentum of object 1 and my final momentum of object 2. So P final 1 plus P final 2. Okay, once again, we are now at a point where we still can't use this equation to make calculations or predictions on actual data. These are just concepts of momentum, and if I've been given the momentum, then I can use this. But we need to go one step further. And we know that the momentum of object 1 is gotten by the mass of object 1 times the velocity initial of object 1. All right, plus the mass of object 2 times the initial velocity of object 2. And then I can do the same thing with these finals. So my mass of object 1 times my final velocity of object 1 plus the mass of object 2 times my final velocity of object 2. And now this equation we can actually use to make predictions on an object's velocity, on an object's direction of motion after a collision. We can also use this to come up with predictions or ascertain data that happened before a collision. And this is very helpful whenever we start doing accident analysis, especially in the world of forensics. So this is actually very helpful, especially whenever you're analyzing car crashes or things where two objects will run into each other, and you can find out what happened before based on what happened after. Okay, using this equation, you can use this on, you will use it on your homework. You will also use it on the exam. Now I want to talk to you about conservation momentum during explosions. Thanks to the slow-mo guys on YouTube who came up with this. If I look at this, notice how during this explosion, water was expelled in both directions. All right? The initial momentum of the water bomb was 0. And then whenever the explosion went off, it actually shot water in both directions, which caused a conservation momentum in the fact that momentum total still equaled 0. Now we see it again in this butane rocket. Okay, if I look at this, as the rocket goes off, it shoots a fast stream of gas out the bottom, which then propels the can up. So initially, the momentum, the total momentum was 0, and then afterwards, with the negative momentum of the gas coming down, it counteracts the positive momentum of the rocket going up.